So I hope you enjoyed the coffee break. We are now moving to the second session of this workshop. Here we'll be talking about renewable hydrogen and potential symbiosis. We'll be talking about the latest research highlights. And in this session, we will expand the lens beyond the OHPERA project, and we will look at complementary research efforts such as alternative hydrogen routes, hybrid systems, integration concepts, and taking scale-up considerations in the end. So I invite you not only to listen to the individual technologies that will be presenting our speakers later on, but also to reflect on and wonder which is their maturity level, which is their integration potential, and in the end, how close they are to this industrial readiness that in the end, every innovative solution needs to take up on the market. So, well, also mention that you can leave your questions on Slido and in the previous session. And it is my pleasure to introduce our first speaker, Dr. Ailbe Manacháin from University College Cork. He will be presenting the project FreeHydroCells, focusing on innovative multi-junction photoelectrochemical cell tandem systems, which are designed for the continuous green hydrogen production. So, Ailbe, the floor is yours.
So thank you. Thank you for the invite to present here today to the organisers. It's a privilege to be here, and it was really nice seeing all the great work in OHPERA. So good luck to you and the rest of that. So today, so I'm the coordinator of this project, FreeHydroCells, and I'm the lead PI as well. And essentially, this is one thing I should point out, that this project is not an EIC project. This is a Cluster 5 Horizon Europe. So it's for the call to look at alternative energies, alternative green energies, and try to give alternative sources for energy to replace fossil fuels. And so it's in this context that it connects to the various EIC projects and activities. The other important thing about FreeHydroCells is that our TRL level objective is TRL 4, but to try to give an alignment for upscaling and commercialization towards TRL 5. So we have very much TRL 5 in our objectives, but it's a proof of concept verification at TRL 4. So, and our duration is slightly less than what you guys have. So we are not as advanced, as far on in the project as where you guys are at the moment. So I have to point out those caveats. The other thing is our main objective is to try to give some pathways, solutions for obviously hydrogen power plants and so on. But we have created our kind of technology so that it can be modularized, so it can be distributed among communities. And we see a great advantage in doing that with all the challenges we have for technical challenges, financial challenges, with transportation infrastructure, the various technical scientific issues there. So we give a vision and a pathway of our kind of technology in that context in this presentation, as well as being applicable to the central energy power plant solution. So, so we kind of all know the challenges that are in front of us at the moment in terms of trying to provide green energy for, you know, to replace the fossil fuels energy that's out there, and trying to meet our targets for the replacing fossil fuel energies to meet our climate goals. We have major challenges there, as you know. So our work is trying to advance that as best we can. And I speak about our objectives in terms of this distributed energy system and our modularized energy system to try to deal with this transportation issue and infrastructure issue. So as well as being centralised, we also are aiming for this distribution vision, and hopefully I can share that vision with you today about that. So I'll talk about the vision, I'll talk about the challenges that we're trying to, and I'll talk about, just at a higher level, about our technical pathway in trying to get there. So these are our main goals. So, so what we're trying to get you to kind of visualize in this case is to imagine this distributed system that could take solar energy and make green hydrogen. And then obviously we all know that hydrogen is a storage of energy, so we can create storage and have it either centralized or locally based. And there's great advantages for locally based hydrogen for resilience for communities, for one. There's also some benefits in terms of storing hydrogen and so on. One of the things we're trying to do in our project is to try and make it versatile for integration with other renewable generation of electricity, say coming from wind or hydro in that sense. So we not only want it to be obviously solar activated, but we want to try and link in with those so that we can try and push it towards a 24/7 operation. We hope that's one of our things we can do in the future. So it's a distributed model, and this model, this vision, if you think of the benefits for the grid, the centralised grid and centralised infrastructure, the benefits are enormous, and we can take all that pressure off the grid, and we can really give resilience and energy democratisation, essentially, to communities. And I see it as a vision that kind of potentially revitalises communities, distributed communities, urban, rural, even cities, in that sense. So this is a kind of technical pathway description of the project, and it's quite high level, so I won't go into the various details of each of the work package or sections, but we start out with novel materials. So we're looking at transition metal dicogenites as a potential solution in this case, and we're looking at PN junctions when we go to the materials integration. And we mix those TMDs, as I call them, with transparent conductive oxides. So we create multi-junctions, PN junctions, of TCOs and TMDs. Then we have quite a novel integrated tandem cell architecture where we're trying to get these materials integration at a thermally compatible level and make a really complex integrated structure. But we're trying to do this by ALD and CVD, so it's cost-effective processing. The whole time we work on these, we're looking at sustainability and cost-effectiveness. So we're trying to increase the efficiency, but keep that cost really low so that we get a good ratio of efficiency to costs. And in parallel to that, we're looking at sustainable materials, replacing maybe critical materials or rare materials with more abundant materials, and we've already been successful in that. Then the idea is to take the cell level and gradually transfer that to the system level. So we have a cell-to-system process in the project, and the idea is to try to maximise the properties of the system that we can see at the cell level and try to get as little loss as possible. You all know that there's a loss. It's quite difficult to prevent loss when you try to scale up from cell to system. We've already went from small area to large area. That's been achieved. We've got our thermal budget a way down for full integration. So there's very significant progress in the project. So we're hoping to be very soon able to benchmark our system, and we're going to be doing an LCA in that benchmarking, and we obviously want to position the project so that we can verify the proof of concept in the project. And as I mentioned, we're trying to position the project very, very well in terms of cost, efficiency, lifetime and so on, so that it's in a position that can be upskilled quite rapidly and without having really to change any of the fundamental processes or activities in the project. So we have that in mind the entire time in doing this project. So I guess I have a video, 45 seconds, and I think I'm okay for time, right? Yeah, so I'd like to show this video just of our vision about the distributed system, because a distributed system is not really something people talk about very much. It's more centralized replacement, and then we have all these issues of transportation and infrastructure that are, the costs are enormous, and the technical and scientific challenges for distributing hydrogen from a central source, storing hydrogen from a central source, are just enormous. So I'd like to present this vision of where we kind of see our objectives in the project, enabling as well as centralised power solution.
Imagine a new, low-cost system deployed in individual homes and communities that produces renewable green energy with the ability to store and manage it locally. It aims to introduce sustainable new materials that harness the power of the sun and drive photoelectrical chemical reactions that split water into a harmless oxygen gas byproduct and hydrogen fuel. Any excess hydrogen produced during the day will be stored locally for use during peak times. By design, this is a distributed system, enabling local communities to look after their own energy production and storage, while countering the causes of climate change and keeping energy costs low, without the need for complex and expensive grid or network infrastructure or transportation.
So that's our vision of this distributed system, and I hope that short video gives some idea of what we're trying to enable. So we're hoping to redefine communities, so for the production, storage and control. Such a distributed implementation would be fundamental for communities in my view. So there'd be a lot of work needed to try to bring communities along with that. I'm here today with colleagues from CEA in France and from UCC Academy and from AMO in Germany. We're very keen on discussing our technology, your technology, and where we can go in the future, right? Because as we've seen in the last question, you know, we're quite early stages of trying to get this technology forward. Cost is a big issue, efficiency, lifetime and so on. And we need to kind of try to, coordinate together, work together. So we are very keen on collaboration going forward, and if anyone is interested in our technology and where we go, please give me a shout, or any of my colleagues here today. So thank you. Questions?
No. Thank you very much, Ailbe, for your presentation. And now we move to David Brust from the Institute of Future Fuels of German Aerospace Center. And David will introduce the project FlowPhotoChem, an integrated system of reactors for solar energy conversion into fuels and value-added chemicals. So, David, please go ahead.
Thanks a lot for the kind introduction. Please excuse my voice. The weather where I'm from is not as sunny as here, so bear with me, please. Okay, I'm David Brust from the German Aerospace Center, and here I will represent the project FlowPhotoChem. So this project is started a little bit earlier, 2020, finished in 24, and it dealt basically with the design operation of an integrated system of modular reactors. So here we have the modular aspect again for the solar energy conversion into fuels and chemicals, where the focus was ethylene as an important precursor for the chemical industry. So the project, it was quite a large consortium consisting of 15 partners from 8 countries, and it was also a quite diverse mix that included universities, included research centers, it also included startup companies, and also a large company, Johnson Matthey, and it was supported by life cycle and sustainability efforts alongside the materials and reactor development. I want to kind of introduce the concept. So we had 3 reactor modules that were powered, 2 of those were powered by direct light input, while 1 of those reactors was driven with electricity input. And we start kind of this cascading process in the front, where we had water splitting with the integrated pack reactor, directly solar driven, producing, of course, the hydrogen and oxygen, where the hydrogen was fed together with CO2 into the second reactor in the chain, the photothermal reactor, that targeted the reverse water gas shift reaction towards carbon monoxide, and methane was also formed as a side product. And at the German Aerospace Center, we provided the solar infrastructure to deliver the concentrated solar irradiation for the first 2 reactors. And the last reactor in the cascade is the electrochemical reactor developed by e-chemicals and the University of Szeged, where the produced carbon monoxide then was reduced towards the target product ethylene with a range of other valuable products also. So now I want to a little bit highlight the individual components in short. So the pack reactor, basically what was achieved in the duration of the project, it was demonstrated that the large scale, so we are talking here kilowatt scale input and also chemical output, the large scale pack reactor, it was demonstrated for a considerable amount of time on the solar dish and produced solar hydrogen reliably. And there are related project publications for reference. Regarding the photothermal reactor, which started out at a lower kind of much lower technology readiness level at the beginning of the project, the main achievement during the project was, of course, the synthesis of suitable catalyst material for the photo-assisted CO2 conversion or hydrogenation, then also the design and fabrication of the photoreactors. And here you can see this kind of scaled up then device mounted in the solar simulator. And here you can see also relevant project publications for reference. And then the electrochemical or EC reactor that was developed by e-chemicals in the University of Szeged. There, the main achievement during the project was the development of devices and the materials to perform the electrochemical reduction of carbon monoxide to valuable multi-carbon products, where, of course, our target product was ethylene. And here you can see the relevant list of related publications. So here are some impressions of how the whole system looked assembled in the solar testing facility at the German Aerospace Center, just up front. So operated was the whole system in a final test campaign over the course of 1 week, and then we had accumulated operating hours for the photoelectrochemical reactor of 24 hours, for the following photothermal reactor of 21.8 hours, and the final electrochemical reactor in the whole cascading integration was operated for close to 14 hours. And this is due to the startup procedure. So once you have this integrated system, you need to make sure you have steady state operation of the process chain, and then you can start to turn on the following reactor. So this is a little bit complication that you run into when you integrate things. You get like a more slow system behavior that you must manage. And here you can see kind of the optical inputs from the front. So these are optics installed to ensure that the simulated solar irradiation will in the end hit the photosensitive surfaces at homogeneous distribution and the correct concentration levels. And this shows kind of the backside view. Here are these xenon lamps with parabolic reflectors. Okay, so just to give you a brief overview of what kind of was recorded during the testing campaign, here you see exemplary results of the first testing day, where basically we recorded all the time series data of the most relevant quantities. So for the photoelectrochemical reactor, you see, of course, total hydrogen production rate, the solar input power. And then you also can see that just a fraction of the overall hydrogen was then utilized due to also scaling discrepancies. So, of course, some reactors were at larger capacities than others, just as a consequence of the level of technical readiness. So overall, you can see that ethylene was produced at the rate of 0.055 moles per hour, and this would correspond to roughly 5 kilograms per year if you would run the system 8 hours per day. So to get an idea of the scaling. So we also, of course, then from these detailed time series data, we can calculate all the efficiencies. So for the PEC, photoelectrochemical reactor, there is a value of 17% of solar to hydrogen based on the enthalpy of reaction. For the photothermal reactor, when you only consider the product CO, we get a value below 1%, and this is kind of indicating already the overall system efficiency. And for the electrochemical reactor, we recorded an efficiency of 11% considering the enthalpy of ethylene formation. And then we end up, when we only consider ethylene as the target product of solar to chemical efficiency of 0.6%, but, and this is important to highlight, if we consider all intermediate or side products in the calculation of efficiency, a much higher number of close to 7% results. Yeah, and maybe you can already just see, I don't want to go into detail, but that there is, due to the cascading of the different reactors, you need to manage kind of non-constant feed streams of intermediate products. So this will impact the performance also. So you can see just an example here, the CO2 the CO production rate here is also correlated to the CO2 inlet stream, and since we had problems of managing like a stable constant stream, this is also reflected, and of course this then translates to the following reactors. So just to point out, there are challenges when you go from individual reactors to system integrated system. Yeah, so I want to conclude. It was a challenging but very, very interesting project where it was shown that, in integrated system for the solar ethylene production, it was demonstrated in a practical environment, and for the first time, such a reactor cascade consisting of these three technologies was demonstrated. And in general, one could say that the feasibility was demonstrated of this approach, and as stated before, the efficiencies, only considering the target product ethylene, was at 0.6%, but much higher efficiency considering all intermediate products of 6.8%. Yeah, what kind of synergies we gained and others also might gain from looking at this project is, of course, these practical conditions matter, and the experience you make when you scale up things, when you integrate reactors, this will really further your understanding and also advance the technology when you tackle those challenges. And regarding scale up, there were many startups involved, so some are also present here in this OHPERA project, and the startups, of course, within the project worked towards commercialization of their technologies, of course, at different stages. So with this, I want to thank you for your attention, a photo of the final project meeting in Cologne back then, and I want to leave here this link. We have a nice project video where you can get some visual impressions of the project. Thank you very much.
Thank you very much, David, for your insights on the FlowPhotoChem project. Our next speaker is Guillermo Figueruelo from Fundación Hidrógeno Aragón and Hydrogen Europe Research. And today, Guillermo will share practical insights on accelerating alkaline water electrolysis technology through research and development, validation, and industrial alignment. So, Guillermo, the floor is yours.
Thank you very much for the kind introduction, and obviously to Lomartov and the rest of the OHPERA partners for the kind invitation. There is no solar hydrogen production in the journey that I want to share with you today. So Aragon Hydrogen Foundation, Fundación Hidrógeno Aragón, is a private research center located in the north of Spain, in Huesca. We have more than 20 years life working and really focused on the development and promotion of R&D and innovation projects on hydrogen and fuel cells. And one of our strengths is the validation of alkaline electrolysis, and this is the journey I want to share with you, this experience I want to share with you today. How we have managed to work on that? Basically via European funding, and mainly inside of the Fuel Cells and Hydrogen Joint Undertaking, former public program working on hydrogen and fuel cells, and the current Clean Hydrogen Partnership. Not in vain, we are the most successful Spanish entity in this European funding program, with more than 40 projects and coordinated 1/4 of them. And personally, as I have been introduced, I'm in the board of Hydrogen Europe Research, which is several partners that are here today are also part of this association, which is compiling all the stakeholders, the research stakeholders in the European hydrogen ecosystem. So what we offer firstly in our facilities, which are kind of singular at the European level, we offer as a research center training. We offer also consulting, and we offer also validation, not only in alkaline electrolysis, which is the main focus today, but also in the injection of hydrogen in the natural gas grid, where we have in our facilities a replication natural gas grid where we operate with mixtures of hydrogen and natural gas, and also with 100% green hydrogen flow. Together with several European TSOs, such as some of our board members in the Aragon Hydrogen Foundation, which is Enagas, and also we offer validation in our refueling station. It is operational for the last 12 years. A dual dispenser on 200 and 350 bar, and currently we have been already more than 1 year indeed in operation of our new hydrogen refueling station operating at 700 bar, which is the new light vehicle standard. So with regard to validation, we inspire and we offer confidence with tried and tested safe products at our facilities, and really focus on the pressurized alkaline electrolysis is what I'm going to talk to you today. We carry out characterization, performance verification, analysis under different conditions, high pressure, high temperature. We are quite flexible there. We also validate innovative ideas, reducing business risks, both to research entities and also to industrial players. We design and perform customized efficiency and durability tests for electrolysis shortage stacks under the harmonized JRC protocols. We will come to this later. And finally, we offer a real scaling up of the technology from validated concept at TRL4 up to operational prototype, first fully approved and tested in a real environment, which is something that we can offer in our facilities, reaching TRL7, so pre-commercial states already. And as mentioned before, well, this journey started 15 years ago and started working under the European program, the Fuel Cells and Hydrogen Undertaking. We have been following several follow-up projects, and the first one was Eligrid. We were contacted by Industry Old Technologies. This is a former Swiss alkaline manufacturer, which was acquired by Sunfire 5 years ago. So 15 years we started working with them, and you will see during the different slides the huge collaboration with other large research centers at European level, but also with different component and stack OEMs, how we collaborate on our facilities. So in the Ligrid project, 15 years ago, we started boosting the alkaline electrolysis performance in our industrial test bench, which is the one that you can see in the picture. We call it industrial because the size is 1.6 meters of diameter, is the proper size that is used currently, or yeah, more or less the figures that are used in between the different OEMs at the industrial scale. But the particularity here in our facilities is that we don't perform tests on the full stack, only in short stack. So we are able to stack from 4 to 7 cells in our facilities to be in a proper amount of power. In this industrial test bench, for instance, we are able to work up to 200 kilowatt pressurized alkaline electrolysis. Again, this is one of the insights today. We operate over 30 bar usually, and the usual figures for alkaline technology 85 degrees. The follow-up project is integration, which started just about when the Ligrid finished. And during that first project, we were aware about the difficulties to work only on the industrial size, let's say. It was not cost effective in terms of movement of material, heat inertia, moving the stack from Switzerland with the aduanas in the middle in each shift of the stack. The weight of the proper stack, it was also difficult to be handled in between our staff. So we decided to go to a lower stage, and we designed by that time the test bench that you can see on the screen. It was designed, built, and currently been operating for more than 8 years in our facilities by our own staff. And at that project, we started with 120 hours dynamic operation that revealed heterogeneous cell degradation, but we also were working on the gas cross-contamination and the thermal management. And as you can see here, again, a strong collaboration not only with component OEMs, but also with IT companies and with research centers. At that time, when we finished that project, there was a third follow-up, which enabled us to, and you have seen in 2011, we started at more or less a lab scale at TRL3. We reached 10 years later in 2021 with the same alkaline OEM, IHT, and we were able to develop and commission an electrolyzer of multi-megawatt, the one that is on the screen, that is working in a facility in Innsbruck, in Austria, is 3.5 megawatts. So in this journey, we were able to scale up the technology from TRL3 to a commercial stage. And now they are selling that product under the brand of Sunfire. We also were called by our colleagues of the JRC to collaborate with them to develop and design somehow an harmonized protocols for testing of low temperature water electrolyzers. This was in 2021. Already published, and you will see there how our references appear and how we have developed these harmonized protocols that are being used from that time to now. What happened after these 3 initial projects and what is currently being ongoing in our facilities? And we needed to somehow twist our innovations. We didn't follow our collaboration with IHT, and we turned to collaborate with new European OEMs. In this case, we started working with green hydrogen systems, They were on bankrupt 2 years ago, and they are now replaced by the Spanish manufacturer Ariema. And we are working on the OHPERA project on the next generation high-pressure alkaline electrolysis. This is, I think that the highest pressure that is going to be achieved in alkaline electrolysis, and we are already in the position to tell you that in this year, in 2026, we are going to be able to reach a hydrogen outlet pressure above 80 bar, and this obviously affects directly to the temperature that is operating inside of the stack, and we are reaching higher temperatures above 100 degrees. And we are also in the right path to arrive to a near zero energy losses. And also running and being tested in our facilities right now, and this is I think I have not mentioned it, but we have coordinated by Aragon Hydrogen Foundation all of these projects, and this is the unique work done that is not being coordinated by ourselves. So we have also this kind of tangible expertise, let's say. And it's Stargate Hydrogen, quite a newcomer in the market from Estonia, the ones that are coordinating the project Endure, in which we are working between TRL 3 and TRL 5 on the enhanced durability of the stacks, trying also to go to PGM-free alkaline stacks, and evaluating how we can make closer alkaline and PEM like performance and very low degradation. And we are validating this, and we have not talked about size of the stacks, but we are using 100 centimeters squares in our facilities, but also 1,000 centimeters squares. We are also quite flexible in the lower TRL test bench, which was designed by ourselves. We are also flexible in between the number of cells that we can stack, in between 4, in between 10. We are able to work there in between 2 kilowatt up to 20 kilowatt. And the main outcome here in these 4 projects that has been happening in our facilities is that the results or the tests that are being developed in the low TRL test bench are replicable, completely reproducible, and happening in the industrial test bench, and also happening in a commercial multi-megawatt electrolyzer. This is one of the main outcomes. Everything is reproducible from this little short stack up to a multi-megawatt industrial stage. And the key milestones as of today, we have already tested and validated 5 different OEM manufacturers alkaline stacks in our facilities from the manufacturers that you can see there. And we are also offering our knowledge in our facilities in different client-to-client or private contracts. The main entities or the main needs that we see right now in the market are coming from component OEMs, obviously also from component and startups, also at a stack level. And it's quite tricky, but also the hydrogen production plant developers are asking to somehow validate what the stack manufacturers are offering them, the warranties, the performance, etc. The EPCs firms and also the early adopter industrial end users are kind of willing to have a second opinion. Obviously, we are eager to collaborate and enlarge our participation and our validation in our facilities in terms of this knowledge that started already 15 years ago. Yeah, thank you very much for your attention.
Thank you very much, Guillermo, for your presentation. Finally, to close this round of presentations, we welcome José Mata from the Institute of Advanced Materials at Universitat Jaume I. He will be presenting the project PECADS, exploring photo and electrocatalytic routes for long-term sustainable hydrogen storage. So, José, the floor is yours.
Thank you very much for this kind of introduction. And first of all, I just want to thank Romartov for making things so easy. It has been just a pleasure just to deal with them. And especially I want to thank all the people from OHPERA, and especially Sixto that just invited us just to present our project in here. So in here, our project, it is called PCATS, and it stands for Photoelectrocatalytic Routes for Long-Term Sustainable Hydrogen Storage. This is not a sister project of OHPERA, that's a problem, but I would say that is a nephew, so still there are some family relationships. So the mission of our project is just to develop efficient ways for hydrogen storage, but our aim is just to store the hydrogen without using hydrogen gas. So just, I will skip a little bit the motivation of our work, and what I want to point out in here, it's only that the use of renewables just require the storage of energy. And the reason because we need some storage is because the most efficient way to produce electricity using renewables is just to inject all the electricity that we produce into the electric grid. However, if we have energy surpluses, as it will happen here in the region of Valencia, that in 10 years we are going to multiply by 20 the energy production using photovoltaics, we will have for sure energy surpluses. For this, we need just to develop efficient ways to store the hydrogen. In here is where the hydrogen enters as a potential or very good energy vector. The main reason, because I think that the hydrogen is a good energy vector, is because when we just recover the energy, we are just obtaining a high amount of energy, but the main reason is because that we are not producing carbon dioxide. So in the end, we have just to store the hydrogen, and hydrogen is a difficult molecule to store. So I have divided in here the different ways to store the hydrogen, just distinguishing between the physical-based methods and the material-based. On the one side, in the physical-based methods, we have the pressurized or the compressed hydrogen gas, the liquefied version, or technologies that just combine pressurization and low temperatures. And on the material-based section, we have different adsorbents. We have metal hydrides that can form strong metal hydrogen bonds. And then we have the liquid inorganic carriers and also the liquid organic carriers. In this talk, I will focus in the use of liquid organic hydrogen carriers, and the reason for that is that it has different advantages. In my opinion, the main important advantages is that we can use the actual infrastructures for the transport and distribution of hydrogen. And this system is safe and secure, so we are dealing with organic compounds. And another reason because it's important is that we are going to store the hydrogen for long periods of time at zero cost. So what we have in here is the technology of the liquid organic hydrogen technology. In here, it represents this technology is composed by two molecules. One molecule is hydrogen lean. It doesn't contain many hydrogen atoms. And there is the counterpart that is the hydrogen-rich molecule. So the conversion between these two species is just related by two chemical reactions. The reactions is the hydrogenation reaction. That is when we just put the hydrogen into our system, and then we have the dehydrogenation process. From a chemical point of view, I like to see this hydrogen storage technology as a reversible reaction, where we have to combine the hydrogen-rich and the hydrogen-lean molecules by these two transformations. In the end, what we have in here is a reversible reaction. And I want to point your attention here that according to thermodynamics, one of these transformations is going to be favored. So in the end, we will always have one transformation that is not going to be facilitated by thermodynamics, which means that in the end, it will produce more cost in the normally in the release of the hydrogen. So we have been working in this technology from the thermal catalytic point of view. And in here, I'm just showing you one example where we use benzylamines or the pair amine nitrile, where we just can store the hydrogen. So this represents the dehydrogenation reaction, where we obtain the hydrogen that is charged in our molecule, and for this transformation, we just develop ruthenium catalysts that perform this reaction in an efficient way. On the other side, we have also the introduction of the green hydrogen into our system, and for this we use nickel catalyst, nickel as catalyst. So using this amine nitrile carrier, we can store up to 5.5% of hydrogen storage capacity. This is a thermal reaction, and we also have the electrochemical part, where we just convert the nitrile into the benzylamine, and we have also developed electrocatalytic processes that convert the benzylamine into the nitrile. So in here, what we want to realize is the cost of the hydrogen, because when we are storing the hydrogen, we need just to perform different transformations. We are using the green hydrogen that is obtained by electrolysis from water, and we still have to convert the hydrogen into our system, and later on another transformation consists in the obtention of this hydrogen. So in the end, we are increasing the cost of the hydrogen. But for that, just pay attention a little bit to the business model. This case was developed by the company Chiyoda. Chiyoda is a company that is from Japan, and they just made an economic evaluation of the production of hydrogen in Japan, or the production of hydrogen in another country where the use of renewables was more favorable. Japan is not a country that has many solar hours per year, so the production of hydrogen is not very convenient. So they established this evaluation, and they observed that using liquid organic hydrogen carriers, the cost of the production of hydrogen in Japan, or compared to Australia, it was reduced by $1 per kilogram. For me, this techno-economic analysis is important, but what is more important is that we have also to consider that the main cost in the hydrogen storage technology is the production of the hydrogen. So we, in order to develop the project package, wanted to reduce this cost. And the way that we are facing how to reduce the cost of hydrogen production and working with our hydrogen gas, it was to combine directly the introduction of the green hydrogen in our liquid organic hydrogen carrier at the same time that we were producing the oxidation of biomass into platform chemicals. In this way, we are not producing hydrogen gas, so we believe that the cost of hydrogen is going to be reduced. So in here, we arrive to the goal of package project. So in this project, we aim to convert the hydrogen lean liquid organic hydrogen carrier into the hydrogen rich, having the hydrogenated molecule through a reduction process. And we are going to put this hydrogen in this molecule using the hydrogen that is obtained from biomass. So at the same time that we are oxidizing the biomass, we obtain platform chemicals. That also represents added value products. So we are going to develop this project using electrocatalysis and photoelectrocatalysis. And this will have an impact in the energy sector, because we are storing the hydrogen, and on the other side, we will have also an impact in the chemical sector, as we are providing chemicals that later on they have different type of applications. So in here is the goal and the results that we have up to now in the PCATS project. On the one side, we are oxidizing the molecule HMF into the FDCA. Pardon me. So this molecule is a very platform molecule, and it has many applications in the development of polymers, or also used as additive in the petrol industry. And on the other side, we are using the paired nitrile benzylamine in order to incorporate our hydrogen. The results that we have up to, so far in the development of the project is that in the conversion of nitrile in the benzylamine, we have conversions and yields close to the 70% with 50% of Faraday efficiency. And in the oxidation compartment, we have quantitative yields, conversion, and Faraday efficiencies. So just to finish, I want to thank all the members of the consortium that involves 7 partners of 4 countries, from the University Jaume I, the Trinity College of Dublin, Fundació Institut Català de Nanociència i Nanotecnologia, Comet Global Innovation, the European Innovation Marketplace, the TIC Energy Gune, and the University of Zurich. And finally, I want to thank all the members of the group from the Universitat Jaume I that we all work at the Institute of Advanced Materials, and this group, or this consortium, is formed by physics, chemists, and engineers. And thank you all you for your very kind attention. Thank you very much.
Thank you very much, Jose, and all the speakers during this session of the workshop. We have now some minutes for questions. If you haven't left your questions on Slido, you can still do it, or you can raise your hand if you are present in the room, and we will pass you the microphone.
Thank you, sorry. For the first presentation, I'm not sure where the presenter... Oh, sorry. So are you doing some kind of social acceptance assessment for... Because for me, household storage of hydrogen is a bit tricky. So are you doing something along this line, like assessing social acceptance of this approach?
We will be doing an LCA of the technology at some point. We probably try and include some social aspects, but it won't be fully encompassing at this TRL level. It would be something that we would like to look into further with collaborations in the project. So the objective of the project doesn't necessarily have to be distributed solution. It could be centralized, but we feel that to overcome some of the challenges that are faced for distribution, we could have a distributed solution to it. But the social implications are quite high, so it's something we need to look into more for sure. Yeah.
Okay, we had a question here in the front row.
Well, thank you very much. This is a question for the last speaker. Has been a very interesting technology what you presented. It's a curious way to obtain the liquid organic carriers. You mentioned that you are using biomass as a source. I understand that you are using biomass instead of water, that is always good, or you are going to use less water. So what type of biomass are you using? Because biomass is a very huge concept.
Well, for the proof of concept, we are starting with the use of hydromethyl furfural, HMF. This is the molecule that we are using right now. But it is expected that if the project goes on, the uses of different types of biomass should be different. But this is the one that we are using now.
Any more questions? Okay, so if there are no more questions, we can move on to the next session, to session 3, that will be moderated by my colleague Marco Bianchini, so I give him the floor. Thank you.